Hello everyone, now we will discuss on the topic tertiary treatment part 3. In the last two classes, we have discussed on the adsorption based and membrane based methods for the tertiary treatment of wastewater and water. Now, we will be discussing on another type of methods which are also used for tertiary treatment, and this method is basically advanced oxidation process. Here we will discuss on advanced oxidation process for water treatment and then working principles, hydroxyl radical production in different advanced oxidation process techniques, light driven AOPs, benzene oxidation by AOPs, that is one example we will discuss, and advantages, disadvantages and prospects. So, this advanced oxidation process includes two terms, one is your advance, another is your oxidation. So, it clearly indicates that oxidation will be there, oxidation of the pollutants will be there and it is of advanced type. That means, conventional oxygen will not be used. Okay. So, here hydroxyl radical is used for this process and hydroxyl radical is generated in situ by different methods. By the use of hydroxyl radical or the production of hydroxyl radical, we get many advantages as shown here. Hydroxyl radical are highly reactive, these are not selective, they can work on all type of molecules, organic, inorganic etc., and easily generated, that can be generated not so easily, but it is not that difficult also, it can be generated easily that way. And powerful oxidants, we will see that this is very powerful oxidant, the hydroxyl radical is, and we will see that hydroxyl radical is very powerful oxidant, and this is short lived and does not make any harm for its application, for the application of the treated water, because these radicals are short lived. And control of rate of reaction is also not that difficult, it controls the rate of reactions, the oxidation rate becomes under control, that is also not that vigorous reaction. So, we will see here advanced oxidation processes are the treatment procedures that generally use the hydroxyl radicals, the ultimate oxidant for the remediation of organic and sometimes inorganic contaminants in wastewater. The process employ ozone, hydrogen peroxide and UV light for the generation of hydroxyl radicals and are also called as in situ chemical oxidation. The photocatalytic oxidation is also under this category, and hydroxyl radicals are highly reactive, short lived and can work on different types of compounds which are less degradable, and different AOP techniques are ozonization, UV, hydrogen peroxide, photocatalytic oxidation, Fenton oxidation etc. So, we will be discussing about all of these techniques. Before that, we will see what is the so important of this advanced oxidation process. So, as we discussed that in tertiary treatment, our objective is to give the complete removal of the residual pollutants which are available after secondary and primary treatment, and in this case the concentration of the pollutants normally is very less, but the presence of some type of pollutants even in trace amount is also not desirable, it creates different health impacts. So, particularly for the removal of this type of pollutants, this advanced oxidation system or advanced oxidation methods are very relevant. For example, say the personal care products which we are using, the residual is coming with the wastewater and getting entry into the water, and that remains even after primary and secondary treatment in very trace concentration, like say some pesticides, biocides, okay, endocrine disruptors, pharmaceutical products, other emerging contaminants. Domestic wastewater becomes more complex and challenging because of the presence of these contaminants, domestic wastewater becomes more complex and challenging in treating with conventional techniques. Okay. So, this is one major trend we are following nowadays, which needs a special attention. On the other way, to ensure the good public health, the stringent regulations are coming gradually. So, the quality parameters are being monitored more closely day by day, and so the removal of the trace amount of the pollutants is very essential in today's scenario. And for this, to take care of these conditions, highest degree of oxidation potential is required to degrade such trace chemicals. Okay. Now, if we see the normally used different oxidizing agent like say HOCl, hydrogen peroxide, ozone, atomic oxygen and hydroxyl radical, out of these the maximum oxidation potential is for hydroxyl radical, that is 2.80 volt. Since oxidation potential for hydroxyl radical is more than any one individual, as mentioned here like say atomic oxygen, this is basically nascent oxygen, and then ozone, hydrogen peroxide, HOCl, we see this is highest. So, thus AOPs are used as a tertiary stage treatment to oxidize the trace contaminants with hydroxyl radicals. So, that is the reason why we expect that most efficient oxidation we can get if we use this hydroxyl radical, which is generated in situ in the reactor. Now, we will see the working principle of this AOPs. So, what will be the steps for the reactions? There are number of steps, and the first step is formation of hydroxyl radical. Then second step is initial attack on target molecules by OH radical and their breakdown to fragments, and third is subsequent attacks by OH dot until ultimate mineralization. So, initially OH radical is formed, second step it attacks the target molecules, then third step consecutive attacks takes place until the molecule is degraded to the smallest form. Now, the mechanism of hydroxyl radical production highly depends on the sort of AOP technique that is used, that we have mentioned different types of techniques. So, for different techniques different mechanisms are there for the production of OH dot or hydroxyl radical. For example, ozonation, UV H2O2, photocatalytic oxidation and Fenton's oxidation rely on different mechanisms of OH dot generation. Here we will see how this OH radical is generated, hydroxyl radical is generated for different process. Different process are UV H2O, UV HOCl, ozone based process, Fenton's oxidation based process and photocatalytic oxidation and light driven processes. In case of UV H2O2, that is in presence of UV, if we use H2O2 in the reactor, then hydroxyl radical is generated that degrades the organic compound or that oxidizes the organic compound. So, what is happening here? We have H2O2, UV light. So, H2O2 is dissociated into two OH radicals, that is homolytic bond cleavage of the OO bond of H2O2, that leads to formation of two OH dot radicals. Okay. Just like this is our H2O2, UV light, it is giving two OH dot. So, this bond is broken and 2 dot is shared, 2 electron is shared with each OH, and that is called OH radical, and this OH radical is reacting with this organic compound, and that is initially it will be attached, then it will be break down continuously. So, bigger molecule to smaller, and then ultimately we will be getting CO2. Okay. So, this is the mechanism through which the OH dot is produced in presence of UV and H2O2 and how the compound is degraded. So, here it is shown that this organic compound is coming from this gas stream and it is coming into the liquid phase, water phase, and that is degraded by this way. Here this graph also shows H2O2 concentration millimole for different type of system where H2O2 is available and UV is available. So, like say H2O2 water system, here UV is not available, UV H2O2, UV and H2O2 both are available. This is phenton, no UV, and UV phenton. In this case phenton is also available, UV is also available. So, this graph shows in case of only UV, but this graph shows H2O2 water. So, if only H2O2 and water is remaining, then the H2O2 concentration is this much. That means, the formation of hydroxyl ion is less, but when we are using the UV or when we are using the phenton or UV phenton. So, when phenton, then we are getting more hydroxyl ion formation and UV phenton both giving the maximum hydroxyl ion production, because UV H2O2 concentration is reduced. That means, that is converted to this type of products, that is hydroxyl radical. So, these are the different methods where the hydroxyl radical are formed, and the extent of hydroxyl radical formation is different, and that depend upon the type of methods which we are following. Now, UV HOCl method we will see, that is also in presence of UV light. Say if HOCl is present in the water, that is hypochlorous acid in water, then this HOCl will be dissociated to OH dot and Cl dot, that is hydroxyl radical and chlorine radical. So, how this can be possible? So, if HOCl is present in the water, so under the presence of UV light it will be dissociated to OH dot and Cl dot, but HOCl in water, how this can be available? We have chloride in the solution. So, if we provide some electrolytic circuit, so then if we provide some voltage, so there will be some conversion of chloride to Cl2, and that Cl2 will be reacting with H2O and give us HOCl and Cl minus. So, then HOCl will in presence of UV light, that will be converted to OH dot and Cl dot. Once OH dot and Cl dot is converted, so the Cl dot can further be reacting with Cl and then it will be Cl minus. So, that will give us Cl2 this moiety, okay, and then that will attack organic compound, and this OH dot will also attack on the organic compound, and the similar type of attack will continue until this complete organic compound is degraded and converted to CO2 and H2O. So, this is the mechanism of the UV HOCl process, and the photolysis of hypochlorous acid and hypochlorite OCl minus produces a suite of reactive oxidants including hydroxyl radical, chlorine radical. Therefore, the addition of light to chlorine disinfection units could effectively convert existing drinking water treatment systems into advanced oxidation process. We have already discussed that in case of conventional treatment or after tertiary treatment we go for disinfection. So, when we use both chlorine and UV, so in that time this type of reaction can take place and disinfection also takes place. So, automatically disinfections and advanced oxidation is taking place in the system when we use this UV and chlorine for the disinfection purpose. Now, we will discuss on AOP with ozone, advanced oxidation process based on application of the ozone. So, ozone based AOP. So, in wastewater ozonation, the amount of ozone which gets dissolved in wastewater is the only reactive ozone and effective on pollutants and contaminants. So, ozone which is coming into the water phase, that will be reacting and that will be generating nascent oxygen. So, we have seen that nascent oxygen is also having very high oxidation potential which is more than the ozone. So, this is considered as very effective agents for the oxidation purpose. So, the reactive ozone when reacts with the pollutants in wastewater gets consumed also. The efficiency of ozonation process also depends upon the efficiency of core wastewater treatment and effective reductions in pollutants. So, whether this ozone only or it is there are some UV or H2O2, so phenton etc. So, depending upon the environment, the efficiency of the hydroxyl radical formation will be varying. So, generally wastewater contains diversified constituents pollutants, out of them ozone reacts with many of them and in the process gets consumed, and the ozone reacts on microorganisms, color, odor, COD, BOD, organics, inorganic, heavy metals, oil and grease, total organic carbon, volatile organic compound etc. And ozone can be used in different way, like say ozone based AOP may be like ozone in presence of UV, ozone in presence of H2O2, ozone in presence of iron 2 and ozone in presence of metal oxide, ozone in presence of photocatalysis, ozone with activated carbon, ozone with sonolysis and ozone with phenton. So, different methods we can adapt using ozone for the advanced oxidation purpose, and in this case we will see the mechanism for the hydroxyl radical formation and the oxidative agents formation. So, O3 plus OH minus reacts and it gives us OH2 minus and O2. Okay. So, reaction between ozone and a hydroxyl ion leads to the formation of H2O2 in charged form. So, this OH2 minus, this is nothing, but if we add H plus, then it will be giving us H2O2. So, this is H2O2 in charged form. So, that is the first step, and then O3 plus HO2, that will give us HO2 dot plus O3 dot minus this species. So, a second ozone molecule reacts with the OH2 minus to produce the ozonide radical, this is, and this ozonide radical further reacts with H plus and gives us OH3 dot. This radical gives to OH upon protonation. So, HO3 dot, that will give us OH dot plus HO2. So, this is if one oxygen is coming out and OH dot we are getting, hydroxyl radical we are getting. So, this is the mechanism through which OH dot is produced in presence of ozone, and we see here ozone in combination with other agents gives better performance. Combination of ozone with other techniques to increase the generation of hydroxyl radical, thereby enhancing the treatment efficiency. Now, phenton based AOP we will see. So, here Fe2 is converted to Fe3. So, in presence of H2O2. So, this is the phenton reagent H2O2 and Fe2, it will be available in the media. So, then Fe2 will be converted to Fe3 plus and OH dot radical plus OH minus. So, initiation of phenton's reagent this is, and then regeneration of Fe2 plus catalyst. So, Fe3 which is produced in the first step, that will be converted to again Fe3 to Fe2 plus, okay. So, plus H2O2, so Fe2 plus HOO dot plus H plus. So, then H2O2 is ultimately giving us OH dot plus HOO dot plus H2O. So, self scavenging and decomposition of H2O2 basically. So, this is the mechanism of phenton based AOP, where we see here OH dot is generated by this reactions with H2O2, and once OH dot is generated, that will be reacting on organic compounds. So, hydroxyl addition, then that will be degrading this like this, and further degradation will come and it will be giving us CO2 and H2O like this, and if it is RH, hydrogen abstraction can take place here. So, then R dot and H2O will form. So, that R dot will further be reacting with this OH dot and like this, and further oxidation will be carried out. So, that way this method will work. Now, we will see photocatalytic oxidation with TiO2. So, in this method, in presence of UV, TiO2 keeps one electron and produces one H plus. So, that is your gap, that is called irradiation of the photocatalytic surface leads to an excited electron and electron gap. So, this is electron gap, it is generated, and this is giving us a valence band H plus, and another electron is generated, that is conduction band. So, these two bands have some energy gap, band gap, that is called. Now, both this E minus will be reacting with oxygen and it will be generating O2 dot minus this moiety, and H dot which is available with this TiO2, that will be helping to produce OH minus as shown here. The TiO2 will be absorbing H2O and then Ti4 plus H2O, that will give Ti4H2O, that is water adsorbs onto the catalyst surface, and then this Ti4H2O with this electron gap. Okay, so, that will give us Ti4OH dot plus H plus. So, on this solid catalyst or TiO2, one OH dot radical is generated. So, that OH dot radical will help to further oxidize the pollutants to the more elemental form. So, this is the mechanism for the photocatalytic oxidation with TiO2. The highly reactive electron gap will react with water. Now, light driven AOPs. So, in case of light driven method, certainly light will be used and different wavelength of light will be used, we will see here in this slide. So, you see that is contaminants of emerging concern, that is CECs. So, treatment of CECs, there are number of processes like UV oxidant, UV ozone, photophenton, photocatalysis. So, all these methods use light, somewhere we use UV and somewhere we use the visible light. So, that way different types of wavelength have been used for different types of methods, and for this the extent of OH radical production or generation is varying in these methods, and some controlling factors are given for these methods like say UV oxidant with reagent dosage, catalyst dosage, they are very important, and UV is used, that is 200 to 300 nanometer wavelength, these rays are used, and UV ozone we use, that is ozone dose and pH is important, UV 185 to 254 nanometer, and then reagent dosage, catalyst dosage, both are very important for photophenton reactions, and in that case light 190 to 900 nanometer is used, and photocatalysis reaction, that is reagent dose and catalyst dose are very important, and light used is 250 to 400 nanometer. Then there are some management concern on this process also, like the detection of light. So, what will be the wavelength, what is the intensity, and there are some issues also, accuracy, sensitivity and responsiveness of these methods. So, these are the challenges or issues we need to address for the successful application of these methods. Now, light driven AOPs, we will be seeing the mechanism. So, here we have seen that some light is used of different wavelength, and then we will see the UV H2O2, UV persulfate, UV chlorine, any methods we have discussed about, and photophenton, homogeneous UV ozone, another type of method, and photophenton, heterogeneous and photocatalysis. All those mechanisms are applicable in presence of light in these methods, or in light driven methods, all these mechanisms are applicable. So, this figure A shows the these three mechanisms UV H2O2. So, that in presence of UV H2O2 will be converted to OH dot. So, UV persulfate in presence of UV H2O2 2 minus will be converted to SO4 dot, and then in UV chlorine HUCl will be converted to Cl dot, so and OH dot. So, this we have discussed already. In case of photophenton, homogeneous and UV ozonation, we see the UV ozone. So, ozone is there and that will give us this OH dot, okay. And in case of homogeneous photophentons, we have Fe2 plus Fe2 and Fe3 in the media. So, that conversion takes place Fe2 to Fe3 and 3 to 2. So, that conversion will take place and we will get the OH dot formation. So, H2O2 will give us OH dot formation, at the same time this conversion will also take place. And so, this type of reaction which we will already have discussed are also applicable for light driven AOPs, when the photophenton homogeneous phase is used, when photophenton heterogeneous phase it is used, that means iron is not in a homogeneous in a liquid solution, it is in heterogeneous phase, that means in a solid or immobilized iron species when it is used. So, this is our iron species immobilized, okay, and this is our base. So, in that case what will be happening? Will be happening that different H2O2 will be converted to OH dot in the presence of this active sites, and this will be dissolution will be there, and then H2O2 formation, H2O2 will be converted to OH dot. Okay. Similarly, this metal which is immobilized here, that will help to capture the organic intermediates. So, then ferro organic compounds, and then that will be further converted to OH dot, and this type of conversions will be there Fe3 to Fe2. Okay. And UV visible light H2O2 OH dot formation will also be possible. So, different types of reactions will be involved in this type of light driven AOPs, and photocatalysis already we have discussed that there will be some valence band and some covalent band. Covalent band will help to produce this moiety, and valence band will be helping to produce OH dot moiety, and these free radicals very powerful, that is nascent oxygen and then OH dot, all are very powerful agent for the oxidation, and the organic compounds will be oxidized. Now, one example we will see here, oxidation of benzene by hydroxyl radicals. So, in this case say this is our benzene, hydroxyl radical is produced. So, it is attached for the first attachment, another is attached at the side by side, we are getting this one. Further attachment of the dash will be abstract, that will abstract one H. So, H2O will form, and this radical it will help to break it. So, there will be breaking of this bond. So, this moiety will form. Further attack of OH dot, it will give this type of compound. So, further attack will continue until we are getting CO2 and H2O, this type of moiety. Now, these methods, the advanced oxidation processes have some advantages and disadvantages, we will discuss those. So, advantages is that this can work on all type of pollutants, even in very small concentration the pollutants are available, but that can be effective. So, that is one major advantage, and most important is that they are not producing any pollutants. Basically, the organic compounds are being oxidized to CO2 and H2O. So, secondary pollutants are not being generated. Okay. So, they can effectively eliminate organic compounds in aqueous phase rather than collecting or transferring pollutants into other type of reactions into another phase. Due to the reactivity of OH dot, it reacts with many aqueous pollutants without discriminating AOPs, and therefore, applicable in many if not all scenarios where many organic contaminants must be removed at the same time. And some heavy metals can also be removed in forms of precipitate, and then in some AOPs designs disinfection can also be achieved, which makes these AOPs an integrated solution to some water quality problems. And since the complete reduction product of OH dot is H2O, AOPs theoretically do not introduce any new hazard substances into the water. So, these are the advantage, and AOPs has some disadvantages also, like most prominently the cost of AOPs is fairly high, since a continuous input of expensive chemical reagent is required to maintain the operation of most AOP system. As a result of their very nature, AOPs require hydroxyl radicals and other reagents proportional to the quantity of contaminants to be removed. So, the selection of the dose etcetera, that is also an issue, and some techniques require pretreatment of wastewater to ensure reliable performance, which could be potentially costly and technically demanding. For instance, the presence of bicarbonate ion can appreciably reduce the concentration of OH dot due to the scavenging processes that yield H2O and a much less reactive species, this one carbonate radical. As a result, bicarbonate must be wiped out from the system or AOPs are compromised. So, in presence of bicarbonate, this system may not be effective. It is not cost effective to use solely AOPs to handle a large amount of wastewater. Instead, AOPs should be deployed in final stage after primary and secondary treatment, have successfully removed a large portion of contaminants. Ongoing research also been done to combine AOPs with biological treatment to bring the cost down. and if we think about the prospects of this process, then we will see the AOPs were first defined in 1987. The field has witnessed a rapid development both in theory and in application. So far TiO2 UV system, H2O2 UV systems and phantom, photophantom, electrophantom systems have received extensive scrutiny. However, there are still many research needs to on these existing AOPs. These are basically on development stage and good amount of research is going on this area. Recent trends are the development of new modified AOPs that are efficient and economical. In fact, there has been some studies that offer constructive solutions. For instance, doping TiO2 with non-metallic elements could possibly enhance the photocatalytic activity, and implementation of ultrasonic treatment could promote the production of hydroxyl radicals. Modified AOPs such as fluidized bed phantom has also shown great potential in terms of degradation performance and economics. So, up to this in this class, thank you very much.